Good morning, dear students. Today we will start with the second part of the second lesson, that is energy, different forms of energy. So you all know what is energy. Energy is the ability to do work. Now there are different forms of energy. The most important one is the mechanical energy. So first one is mechanical energy. So mechanical energy is the energy possessed by a body due to position or rest, and the energy possessed by the body due to motion. So basically mechanical energy is together the potential energy and the kinetic energy. So mechanical energy is made up of two kinds of energy: potential energy and kinetic energy. Now we discuss the first one, potential energy. What is potential energy? The energy due to the state of body or due to its position. This is known as potential energy. So there are basically two kinds of potential energy. The first one is the gravitational potential energy and the second one is the elastic potential energy. Now when we talk about gravitational potential energy, it is the energy required to do work against the gravity. Whatever amount of work is being done in raising an object to a height, that work is stored in the form of gravitational potential energy. Okay, so work done in moving an object against the gravity is stored in the form of gravitational potential energy, that is equal to mgh. Similarly, there is elastic potential energy. What is elastic potential energy? When a rubber string is being stretched or being pulled, then the amount of energy stored in this stretched elastic is known as elastic potential energy. Other examples can be winding of the key of the clock. When you wind the key, the elastic potential energy is stored in the key. So there is an amount of work done, certain amount of work is being done in binding. When it unbinds, when the key unwinds, then in that case what happens? It moves the hands of the clock. So whatever energy that was stored in the winding of the key of the clock, the same amount of energy is released out when the needles of the clock rotate. Similarly, when we compress the springs of a sofa or any toy like ping pong, and compressed spring stores energy. There is a certain amount of work done in compressing the springs. The work energy is stored in this compressed spring, and when we release, then it throws the ball out of the cone that contains the ping pong. Now we will derive the gravitational potential energy. Gravitational potential energy is the amount of work done in moving an object from infinity to a given point near the surface of the earth. We consider that the point of the force of attraction due to gravity at infinity is 0. So when we bring a body from infinity to a certain point near the earth, there is certain amount of work done. This work done is stored in the form of potential energy. Okay, consider a body of mass m. Let us consider a body of mass m. Let there be a body of mass m. It has to be raised to a certain height h against the force of gravity. So the work is to be done. The work now is being done against gravity. Work done is against gravity. Work done का formula क्या होता है? Work done is equal to F into S. What is F? Force. equivalent force equivalent to the weight of the body will be required to lift the body in the upward direction. So force will be equal to weight mg, and the displacement is vertical height h. So displacement is h. Now this much amount of work is being done in lifting a body from the ground to a certain height. This work done is equal to the energy that is stored in the body when it is raised to a height h. This is known as potential energy, represented by the symbol U. U equal to mgh. Now there is one thing that is to be understood. When we say U equal to mgh, this h is basically the increase or change in height. When we define potential energy, it is the amount of work done in moving an object from the center of the earth. And when we talk about center of the earth, the distance of all object from the center of the earth for every body will remain the same. Now, if we consider this to be the center of the earth, then the work done will be equal to mg r plus h. U1, and from the surface of the earth U2 will be equal to mg h. Now delta U will be equal to U1 minus U2 equal to mg h. So basically we consider the ground level, the surface of the earth. The surface of the earth, from here whatever height is being raised and whatever amount of work is being done in raising that body to a certain height h, that work is really the change in the potential energy. Because actually the potential energy has to be measured from the center of the earth. But from the center to the surface, the same amount of work will be done for the same mass. Same amount of work will be done for the same mass every time it is being raised to a different height of the surface of the earth. So this has been explained here. Suppose the body has been taken from the center of the earth. This is the center of the earth. Then from this center of the earth to this height, it will do mg r plus h work. And from the center, from the surface of the earth, it will do only mg h. Now the change will be mg r. That is the difference r plus h minus and up to this one mg r. So change will be equal to mg h. Okay, from up to the center and from center to the surface, whatever is the difference, this is the net difference. So this is equal to mg h. Now if a body is being thrown in the upward direction, then the height is increasing from the surface of the earth. Then the work done is positive. The potential energy is positive. And if the body is falling down, it is coming down, then the height is decreasing. So the body is losing its potential energy. So the height is less. When the height is decreasing, the potential energy is decreasing. The potential energy is coming down, is changing. So a body is falling from h1 height to h2 height. Then the change in potential energy will be equal to mg h1 minus h2. Okay, this is delta U. Okay, now we'll discuss kinetic energy. Kinetic energy is the energy due to motion. The energy due to motion is known as kinetic energy. Now we'll derive out the expression for the kinetic energy. Let us consider a body of mass m placed here. M. There is a force F that is acting on the body. There is a force F that is acting on the body. Now this body is initially moving with the velocity u. And there is a retarding force acting in this direction. This is moving in this direction. So there is a force that is acting in the opposite direction, and it brings the body to a halt. So finally here the velocity becomes 0. V equal to 0. Okay. So there is a force that is acting on an object that is bringing the body to the rest. Now what will happen? when the velocity changes from certain velocity v to 0, it does certain amount of work. Let us calculate out the work done by a body before coming to rest. So work done will be equal to force into displacement. Work done equal to force into displacement. Now what is force? Force is equal to ma. Force is equal to ma. Okay. And displacement s. So we will calculate out s. You have to find out. So we use the equation or linear equation of motion v square equal to u square minus 2as. Why minus? Because it is coming to halt. So s is equal to v square u square minus u square minus v square upon 2a. Okay. Now we substitute this value here. W equal to, instead of f we write ma, and here u square minus v square upon 2a. Since the force is a retarding force, we can put here minus, so here also minus. A and a cancelled out, and value of u was equal to 0. So we get here 1 by 2 mv square. So kinetic energy is equal to 1 by 2 mv square. This is the expression for kinetic energy. It is equal to 1 by 2 mv square, or half mv square. Now we will establish a relationship between kinetic energy and linear momentum. Now what is linear momentum? Linear momentum is the product of mass and velocity, represented by the letter P, a vector quantity, mass into velocity. And what is kinetic energy? Kinetic energy is equal to half mv square. We need to find out the relationship between these two. So instead of m, we can write v. Instead of v, we will put p. V is equal to p upon m. So v square, we have relation here, kinetic energy equal to half m into p square upon m square. एक m यहाँ से हट गया. K is equal to p square upon 2m, or P is equal to under root 2mk. This is the relationship between the kinetic energy and the linear momentum. Okay, P is equal to under root 2mk, or K is equal to p square upon 2m. Now we have two cases. Case number 1, let us have two bodies A and B having masses small m and capital M. These two bodies have got same momentum P. We will find out the relationship between the kinetic energies of these two bodies. So kinetic energy relation is P square upon 2m. So we will find out the ratio of kinetic energy of A to kinetic energy of B. P square upon 2 into small m upon P square upon 2 into capital M. So P square cancel out, 2 so 2 cancel out. It is equal to capital M upon small m. So if two objects have got same kinetic energy, same potential, if two bodies have got same masses, different masses but same momentum, two bodies have got same momentum, then the ratio of the kinetic energy is in the inverse ratio of their masses. Okay, this is inverse ratio. What A का mass क्या था? Small m, it is down, and B का mass क्या था? Capital M, it is up. So the kinetic energies will be in the inverse ratio of their masses. This is case number 1. Case number 2, again we have got two objects A and B having masses small m and capital M. This time their kinetic energies are same. Kinetic energy is same, K, and we have to find out the ratio of their momentum. So let the moment of A upon PB. This will be equal to under root 2mk upon under root 2m capital M into K. Now K से K cancel, root 2 से root 2 cancel. This is equal to under root of small n upon capital N. So the ratios of the momenta will be in the square root of their masses, m and m, capital M and small m. Next we have work energy theorem. The statement for work energy theorem is written here. W is equal to delta K, that is change in kinetic energy. Now according to the work energy theorem, the change in kinetic energy is equal to the work done in changing the kinetic energy. Okay, the change in kinetic energy of a moving body is equal to the work done in changing the kinetic energy, or work done in increasing the speed of the body in its own direction. For this explanation proof, let us consider a body of mass m. There is a force mass m moving with u velocity. What is u here? U is the initial velocity. And we apply a force in the direction of motion. So direction of motion was this side only, and we have applied the force in the same direction. What is the result of the force? The motion will get accelerated. It will become an accelerated motion, because earlier it was moving with u velocity. There is a force that is applied. Now force results in acceleration. So there will be an acceleration in this object, and we find that it gets displaced from s distance. S is the displacement when the velocity becomes v. Now we will find out the work done by this force in changing its velocity from u to v, or changing its kinetic energy from half mu square to half mv square. Let us find out the work done. So formula for work done is W equal to F into S. Force is equal to ma. Okay, this is a force that is equivalent, and S we have to find out. Now S we find out from the equation of motion. V square is equal to u square plus 2as. So v square minus u square equal to 2as, and S is equal to v square minus u square upon 2a. We substitute the value here, ma into v square minus u square upon 2a. A is cancelled out. Now we substitute half mv square minus half mu square. This is equal to final kinetic energy minus initial kinetic energy. That is, work done is equal to change in kinetic energy. Work done is equal to change in kinetic energy. Thank you.